Hey guys, I got a little bit carried away with this one. I got one of those drawing tablets and I was super excited to maybe make a more educational video, so I hope you enjoyed this format. I know it's a bit of a longer video, but I put chapters in the description, so I really hope you enjoyed this one. Also, I'll tell you a story from an interview with a backend candidate we had and why it's important to understand what different databases are made for. And also, I don't claim to be a database expert, but hey, I'm better than Devin, hopefully. Alright, so let's talk about SQL databases first. So they're divided into two main groups, row-based and column-based. So with row-based databases, as the name suggests, they store data about a single entity in a row in a table. And then the properties of that entity are actually stored in separate columns. But the reason they're called row-based is that all attributes of a given row are actually stored together on disk. And this is very important when you think about the ways you can use this kind of database. But before we go into that, it's worth remembering when these databases were invented in the first place. And that was in the time when actually disk space was quite limited. So what you will often hear when people talk about SQL databases and specifically row-based databases is that they do something called normalization. So for example, let's imagine you have a page for a product on a e-commerce website. So let's say you have your picture over here, the title of the product, price, and then some description and maybe seller information over here. In a normalized database, what you're trying to do is get rid of any kind of duplication in the data. So you will store everything exactly once. So let's focus on this seller. Maybe this is a seller name. Now, if this seller has more than one product, let's say they have all of these products in a database, you don't want to store the seller's name together with the properties of that product because that would lead to data duplication. So what do? You actually create one table for the product information like title, price, etc. And then you create another table that is for the seller. And then when you need to display this page, you actually do something called a join query. So you basically join these two tables to produce the information that you need to show the page. So the main thing to remember is that this database structure, specifically normalized, is optimized for writing data and optimized for preserving disk space. But when the time comes to actually present information from the database, you would have to resort to a more complicated query to read the data. Now, another characteristic of these databases is that they support something called transactions. And what transactions allow you to do is, let's imagine you're trying to edit this page and that there's one save button right here. So you might change the seller name, but also the title of the product. Now, ideally, you would want to be able to update one row here that corresponds to the product information and one row here that corresponds to the seller information at the same time. And also, you ideally want both of those operations to either succeed together or fail together. And this is what transactions allow you to do. Now, transactions are a very powerful tool, but they can impact the database's performance because the database has to keep track of all the transaction operations that you're trying to do at the same time and potentially also avoid any conflicts. And row-based SQL databases have been used very successfully for a long time. There is one use case that they are not really great at, and this is analytical workloads. And this is where column-based databases really come into play. So what are analytical workloads? So let's imagine you have a pretty large table. In enterprise applications, it's not really unthinkable to have even 100 columns. But what if for your query, you're really only interested in a handful? Now, a row-based SQL database would have to read entire rows regardless of how many columns you're interested in. And if your table is very large, this can be very inefficient. So a column-based database actually stores the data for a given column in its own location on the disk, and other columns are stored separately. This way, if you're only interested maybe to compute a sum of a given column, the database loads only that column from disk and discards everything else. Whereas row-based SQL databases find it very hard to isolate data of a single column in a very efficient way. However, on the flip side, column-based databases actually have more work to do if you're trying to update an existing entity or even create a new row, because for every single attribute or column of that entity, it will have to write into separate locations on disk, which then makes it difficult to do transactions and other things that row-based databases can easily support. So famous row-based databases are Postgres, MySQL, SQLite, and others. And for column-based, we have Bigtable from Google, we have Cassandra, and so on. Okay, so we covered SQL databases from both the perspective of row-based and column-based, but what about NoSQL? Alright, NoSQL is a much broader category of databases, but in this video I want to cover two of the most commonly used. First off, document databases. Now again, I want to give you some context on why exactly people invented them in the first place and what problem were they trying to solve. So let's go back to that e-commerce product page and let's think about something at scale like Amazon. So again, we have the picture, title, price, the seller information, and some description. Now what people at Amazon and all of these other e-commerce stores started to see is that there is a pattern. And that is that generally speaking, we have many more reads than writes. So in other words, if we're dealing with a very popular product on Amazon, this page might get shown millions of times to the end user, whereas it might actually never be updated in a given month, or maybe very few times in total. So if you use something like a SQL database and you actually normalize your information, you're going to be using all of these complex join queries all the time, and this will dramatically hurt your performance, because the performance that you really care about is the page load speed, because we all know that the faster the page loads, the higher the chance that the user is actually going to buy anything at all. So how do you optimize for page load speeds? So let's think about the structure of this page. What if, instead of doing a join query to pull information from many different sources, we actually store all of the information that we need for the page in a single entity in a database? And so this one entity actually contains information for both the product but also the seller, and it's simply stored as one large JSON object. And whenever you need to load that page, you only do one read. And this is where the majority of the performance benefits of NoSQL databases come from. It's the simple fact that all the information you need to load the page is already pre-aggregated for you in a way. And this is where we come to the story about that interview that I mentioned. We had a guy come into the interview and we gave him a sample problem, and he just said, well, here naturally I will use a NoSQL database because NoSQL databases are faster. But in reality, NoSQL databases, specifically document databases, are not necessarily faster if you're just comparing reading a single entity. Instead, they are only faster if you store all of the information you need for a given page in one object. In other words, if you use a NoSQL database in the same way that you would use a SQL database, so you store your information in many different places, and you still need to make 10 different reads just to show this page, a NoSQL database is not going to be any faster. And now because you don't really need to join data, there are ways that you can optimize your storage layer for horizontal scaling, and people call this sharding. Now, sharding simply means that if you have more than one database server, you can store a subset of your documents on one node and the next subset on another node. And the reason you can do that is that when you need to read that one document, it will only ever belong to one of the shards. And that way, if you have many reads, millions of reads, for example, as Amazon has, they are actually spreading the load across these different shards. And this is what gives them the performance to run the website at great scale. Now, when you store data in such a way that you have perhaps the seller information copied across all the products of that seller, we call that denormalized data, as opposed to normalized data that you have in your row-based SQL databases. And the main thing with denormalized data is that it makes your write operations more complex. So if the seller changes their name, you will have to update every single product document for that seller. But still, people choose to make that trade-off because when you have millions of reads and only a few updates here and there, it is not a big deal to do multiple writes when you need to. Alright, let's talk about streaming databases, and these are kind of the most interesting ones if you're doing something like microservices. But in general, if you have more than one service that need to somehow exchange data between one another, you can either send the data directly, and in a case where you have a producer-consumer configuration, and let's say that you have more than one consumer, this puts the burden on the producer to understand and know at any given moment in time who the consumers are. But also also, in the case that one of the consumers is down, maybe you're doing a deployment or something, the producer again has to worry about some kind of a retry mechanism or some other way to ensure that the message is actually delivered. And so this naive approach can get very complex very quickly. To solve that problem, what you actually do is between your producer and your consumer, you put something like a queue. And this queue is actually a streaming database where a producer can simply save into this database, and the database will ensure that the messages are delivered to any consumers on the other end. And you might have many consumers. Each consumer can actually subscribe to the database, thus relieving the producer from the burden of having to know who the consumers are. And so if one of the consumers is down, for example this one, the database will actually keep track of all the messages that were sent, and once this guy comes back online, the database will actually relay the messages and the consumer can just carry on as usual. The producer is never made aware that this even happened, and that way both the producer and the consumer can be much simpler in their implementation. So for streaming databases, one of the most popular ones is of course Kafka. But we also have SQS from Amazon, and then we also have Google PubSub and others. So this is basically the 4 main types of databases that I always think about when I'm starting a new project. There are other ones specifically in the NoSQL category, like vector databases or graph databases, but this video would get very long if I try to cover all of them. If you're interested, make sure to let me know in the comments, leave a like and subscribe, and I'll see you in the next one.